So now we finally get to use the second part of the fundamental theorem of calculus to evaluate a definite integral. So here I have a reminder of what the second part of the fundamental theorem of calculus says. The integral from a to b of a function equals an antiderivative evaluated at the upper limit of the integration minus the same antiderivative evaluated at the lower limit of integration. So what we end up having is a way to evaluate integrals without using geometric properties to determine areas of shapes, or using the limit definition of an integral where we take the limit of the sums of the areas of the rectangles. So let's see how to do it. Evaluate this integral. I want to find the area under the function x squared from 1 to 4, the integral from 1 to 4 of x squared with respect to x. And so what we can do is the antiderivative, so this would equal the antiderivative of x squared would be 1/3 x cubed plus some constant c. So this is like big F of x, the antiderivative of x squared. Now what we want to do is evaluate this antiderivative on the limits of integration 1 and 4. So one way to write that is to put this in brackets and then write a 1 down here and a 4 up here. And those are x values. And what this literally means is plug 4 into this. Plug 4 in. Doesn't affect the constant. And then subtract what you get when you plug in the 1. So it's the value of the function at the upper limit 4 minus the value of the function at the lower limit 1. And then you simplify this. Of course, your constant's going to cancel out when you subtract. And for that reason, when you do your antiderivative, it's not necessary here to write your constant. Because when you actually evaluate the integral, when you evaluate 1 and 4 and subtract, the constant always goes away. I do recommend writing it, however, so that later on you don't forget that when you take an antiderivative, there is a constant built in. So what we get is 64/3 minus 1/3, which is 63/3, or just 21. So the area under the x squared function from 1 to 4, if you were to look at this, x squared, here's 1, here's 4. At 1, x squared is 1 high. At 4, x squared is 16 high, and it's concave up like this. So this area under the x squared curve from 1 to 4, that area is 21 units squared. So that's much better, some would say, than using the limit definition of integrals to evaluate this value. Here's an example where we can't use the second part of the fundamental theorem of calculus. If I want to evaluate the integral from 2 to 7 of the square root x minus 5 with respect to x, I can't do that because this function is not continuous on the interval 2 to 7, right? However, if you were to graph this function, it looks something like this. So this function is continuous from 5 on. So if you think of this as being the area under this function between 2 and 7, well, the area from 2 to 5 is 0 because the function's not even defined. So you could say then this would equal the integral from 5 to 7 of this square root function with respect to x. And then you'd be looking for the antiderivative of a square root function. And so what we might do is write this as x minus 5 to the 1/2. And the antiderivative of this would be x minus 5. We'd have to raise the exponent by 1, so it'd be 3/2. And then if I were to take the derivative, I'd drop this down. I need this to be 2/3, so that it would multiply by the 3/2 to give me the 1 that's here. So that's the antiderivative plus some constant, and then I'd want to evaluate this at the limits of integration 5 and 7. So I'd plug in the 7 first, and I would get 7 minus 5, which is 2 to the 3/2. So I'd have 2/3 times 2 to the 3/2 plus c, minus, if I plug in the 5 in, of course that is just 0 plus c. The c's cancel, the 0's gone, and my area just ends up being 2/3 times 2 to the 3/2, which you could use a calculator, and that would be the area between 5 and 7 under this square root function.